Okay, so first, extreme value theorem. The whole purpose of extreme value theorem is to identify the highest and lowest y values of a closed interval, but without the use of a graph, just relying on information from critical points. So first, make sure that you create a statement saying that the function is continuous on the closed interval. And the way you find critical points is from f prime. So either set the numerator or the denominator of f prime equal to 0 and consider all the valid critical points that lie inside the interval. And then once you find your critical points and your endpoints, plug them back into the original function and then compare their y values. Highest y value is your absolute max. Lowest y value is your absolute min. Okay. Mean value theorem. The whole purpose of mean value theorem is trying to ask, where is the graph going to experience the same slope as the average rate of change? So it's basically, where is the average rate of change equaling the instantaneous rate of change? So we basically set the slope between the endpoints equal to the derivative. And when we solve for x, we can identify and locate that position where that steepness is going to match the steepness between the endpoints. Make sure you write out your conditions for mean value theorem. Function is continuous on the closed interval, differentiable on the open. So make sure you take care of your algebraic steps before you do your calculus. Okay, don't find your derivative first. I think that messes up with the steps that you're going to do. So take your steps to find your order pair, find your slope between endpoints, get that algebra out of the way, then find the derivative, and then you can set that derivative equal to that slope. So again, mean value theorem is where your average rate of change is equivalent to your instantaneous rate of change. Okay. Rolle's theorem is essentially the same thing as mean value theorem. It's just that in order, rather than looking for just any average rate of change, it's where the average rate of change is equal to 0. Okay, so trying to figure out where's the instantaneous rate of change equal to a slope 0. But in order to guarantee a slope 0, my y values have to be the exact same. So we're still finding slope between the endpoints, but we just need that y values to be the same to force that average rate of change to be 0. And then we go through the same steps. Set f prime equal to 0. In this case, it's always going to be equal to 0 if it's Rolle's theorem. Okay, so that's what we're trying to target here. But in order for a slope 0 to be guaranteed, the endpoints have to exhibit the same y values. So conditions are very similar. Continuous on the bracket, differentiable on the open parentheses. And then our endpoints have to produce the same y values.
You have to do like a statement, like a normal statement.
Not afterwards. Just make sure your statement comes beforehand with your conditions.
Okay, but like after, if like once I get the value C, I don't have to do.
Right. You don't have to say by mean value theorem, so you don't have to do that.
Okay.
Yeah. Yeah. So no, yeah, in that case, in that sense, no justification needed for MVT, Rolle's, or EVT. Your steps is your justification. Okay, so let's try number 1. Apply mean value theorem to find when the instantaneous rate of change will equal the average rate of change on the interval from 1 to 3. So focus on your average rate of change first. Find your order pair, find your slope. Then worry about the instantaneous rate of change. Then worry about your derivative. And then you can set those equal to each other. But make sure also that you list out your conditions, because if we want mean value theorem to be applied, continuous and differentiable conditions have to stand. questions about the steps from email? Number two, you're going to apply extreme value theorem. But make sure you identify your condition. The only condition for extreme value theorem is the continuity portion.
Why you said C was it two?
Oh, that C is another way of saying that's my answer. That's my X value.
So you don't need to find the Y value.
Uh, Find when? No, we don't find the Y value. But if it's asking for the full ordered pair, then you can plug 2 back into the original function.
But if you find like the order pair, would you get points off?
No, that's fine. That's fine. But for EVT, I'm looking for the Y value. EVT is Y value. This one, it's not as specific. So here we're just looking for the C value. Yeah.
Concavity, you have to write justification statement
For what?
for concavity.
Yes, yeah. So intervals of increase, decrease, relative max, relative min, POI, concavity, yes, justification.
Okay.
Make sure you include because statements. Yeah. Number two, just watch out for critical points that lie outside the bounds. Right? Our problem is only contained to what's between the endpoints. So any critical points that's outside the interval is not part of our solution. And the focus is the Y value, so make sure you just present the Y value, not the order pair.
So we get
Yes, yeah. Yeah, and just to kind of let you know that, this word value means Y value for AP. Okay, so you wish that they would just be more clear and say Y value, but that word value means Y value.
even if it's outside the interval, you still write full solutions.
Oh, it's outside the interval for this one, but the 16 for this one still stands. Yeah. So, yeah.
So do you need to find like,
Yeah, I shouldn't have even included this. It wasn't until afterwards, I realized it was outside interval, so I crossed it out. But I shouldn't have even included it. I should just tested 0, 2, and 4 and then stop there.
Like, so if something's outside the interval, do you just plug in every single other value?
Okay, you're only considering endpoints and valid critical points. So you're always gonna test 0 and 4, and you're always gonna test a critical point that does lie inside the interval. So, yeah, make sure you don't test every number inside the interval, that you're testing just the endpoints and a valid critical value. Okay, number 3, intervals of concavity. This is moving into the second derivative function, second derivative sine line. And then making your justifications.
Points of inflection can't be shut off short term.
Yes, point of inflection can be sharp turns.
They can't.
They can.
Okay.
They can be sharp turns. So it's possible that yeah, it's possible that the concavity, that the second derivative value at that point is undefined. But that point can still be a point of inflection. Any questions with the first page? I just want to make sure I answer this question about the homework. For number one. This was the largest area of a rectangle inside this parabola. So if you draw a parabola and if you imagine a rectangle inside, this is X distance away, which means that this is X distance away. And then the height is Y, which is going to be hitting at a point on the curve. So your area is 2x times y. And then your substitution help comes from the y equals 9 minus x squared. So you insert that in. And then you just clean this up, find the derivative, solve for x, and then plug back into your dimension equation. Question. Okay. So make sure got your question answered. Okay.
There's also an ellipse problem.
Yeah, that ellipse problem. Let me work on that and I'll present that as well. Okay, let's go to page 2. If you guys can make an adjustment with the curve, I didn't mean for the curve to have these sharp turns because it makes for the derivative graphs to be a little bit strange to graph. So if you guys can just smooth those out. So no sharp turns, smooth curve all the way through. Oh, sorry, guys, I made an adjustment to this graph. So the range, I meant for it to say from -4 to 3. So it's gonna dip down, but it's not dip as low as -7. So. Okay, but first, knowing that this is the derivative graph, we can make our proper reads. Above the x-axis is slope positive. Below the x-axis is negative slope. On the x-axis is slope 0. So from -4 to 4, those are my endpoints there. I'm expecting, so decreasing slope, positive slope, negative slope, positive slope. Relative min, relative max, relative min. And then for your concavity sign line, the peaks and valleys will be your points of inflection, and then your positive and negative slopes will be your positive negative slopes will be your concave up or concave down.
Wait, how's the F prime graph domain different from the regular F(x) graph? There's like arrows. Okay.
Yeah, so I just we're gonna ignore the arrows and we're just gonna look at the graph between -4 and 4.
Okay.
Yeah.
I put negative infinity, like that's different,
Okay.
or in decreasing.
Right. Yeah, 3 can be considered as a critical point, but it's neither a max or a min. So it wouldn't be incorrect if you wanted to put a critical point there and do concave up on both sides, but we could also just let it pass. Yeah, but it's not going to create a point of inflection. But technically, yes, it is a critical point. Okay. And then your because statements are, well, first your intervals and everything is going to just come from your concavity sign line and your F prime sign line. And then make sure that you're writing out your because statements.
Since I don't know the y value of the relative max, can I just make it up within the domain or within the domain?
Exactly, right. So you know that your relative max is going to have to be 3, has to hit a y value of 3 in order for that range to hit. Right. So I'll draw the graph with you. Okay, you're talking about the f of x graph, right?
Yes.
Okay. And right now, when you draw the f of x graph, don't worry about the concavity, just worry about the f prime, the slope. So we know that we're starting at -4, 3. I know I'm going to decrease in this interval to some y value. But then it's going to rise up to a relative max at -1, which can be either 3 but it can't be higher than 3. And that's going to decrease all the way down to a relative minimum. We have a range from -4 to 3, so. Gotta go all the way down here before it rises again. So whatever we do with our graph, you have to just make sure that it kind of fits in that interval range that is provided for you. Your second derivative graph is just going to be built off of your concavity sine line. X-intercepts above axis, below x-axis, above x-axis.
The Y value on the graph doesn't have to be like all the way down, as long as it's the critical numbers you get.
It does because I did provide you a range. So. And you can always sketch the graph first and then adjust it by either pulling it or pushing it so that it fits in that range I gave you. Yeah. And one thing to keep in mind is that every time you find the derivative, at least for the graphs I give you, there's going to be less curves the lower down in your derivative, right? So if you're producing more curves with your second derivative than your first derivative, then something is off, right? So your second derivative is going to be a lower degree, so there can be less change in direction.
That double prime graph has the same domain, right?
Yes. Okay, let me review second derivative test. Second derivative test is not the same thing as the test for concavity. You're using the second derivative function to gather information about relative max, relative min. So what we do for a second derivative test, we find f prime. We find the critical points at the f prime stage, and then we gather our candidates. Then you take your f prime candidates, plug them into the second derivative function, and then look to see what you get. Do you get a positive second derivative value or a negative second derivative value? So let's say candidate x equals a gets inserted into the second derivative, and that gave me positive. Positive second derivative means concave up. Concave up looks like this. Concave up will produce a relative minimum. So let's say candidate x equals b from f prime gets inserted into the second derivative function. Let's say that produced a negative value. A negative value from the second derivative standpoint would be concave down. Concave down looks like this. Concave down will go from that. Okay, so try that with number 5. Okay, everybody good with finding these candidates from f prime? So find your second derivative function and then insert the 7/6, 11/6 into G double prime, and then look to see whether it's positive or negative value. Okay. The actual value for the second derivative is not that important. It's the fact whether it's positive or negative. Cosine of 7.5 or 6. It's going to be negative root 3 over 2. Negative times negative is positive, so concave up means relative minimum. And then cosine of 11^6, that's positive, but there's a negative 2 in front, so negative times positive is negative. Concave down means there's a relative max.
You have to say concave up because G double prime is positive or but you can say concave up.
Say it again?
Like, do you have to justify concave up before like assuming it's true or
No, I just wanted to convince you that it's relative min, but you could jump from here to relative min if you want.
okay?
Yeah.
I can say relative min at there because that double prime is positive.
Yes, you can.
Okay.
I'm saying concave up because a lot of students associate positive with max and negative with. So I want to keep reminding us that, okay, if you can visualize the shape, then you're going to have an easier time of avoiding mistake. Okay, let's do one more. So the graph of f is shown. Which of the following could be the graph of the derivative of f? So without even looking at my choices, I just want to create my own version. So here's my slope sine line. My slope sine line was just going to follow exactly as how my graph's going to look. It's going to rise to some point. That point is not identified. I'm going to call it point C. And it's going to fall after that. Now, along the way, I can also tell that my concavity changes, right? Concave up to concave down, concave down, concave up. So hypothetically, I'm going to call points B and D as my points of inflection. Concave up, concave down, concave up. So if I want to translate this onto an F prime graph, I got to have above the x-axis representing positive slope, below the x-axis representing negative slope, and then point C as my relative max. So left of point C, I want my graph to be above the x-axis, to the right of point C, below the x-axis. But I also gathered information about points of inflection. So I know that point B and D will be the peaks and valleys of my F prime graph. So concave up, positive slope, concave down, negative slope, concave up, positive slope. So this is how I created my graph without looking at my answer choices. And then with that, choice A matched best with the graph I created. Okay, we'll continue with this review tomorrow. Okay, check your calendar. I think you guys will finish up on the AP problems in your packet. All right, come get your phones. Yes.